actually hurt. My never hurts.
Okay, section 6-7, theorems about roots of polynomial equations. So we've talked a lot about different methods for solving. Do you remember any of them? Like off the top of your head, what we called them?
We did the last section.
Solving, remember when it was equal to 0, so blah, 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 some kind of x to the nth plus x to the n minus 1 plus x to the n minus 2, and so on, right?
Yeah.
What were some ways that we learned to solve these?
You set it equal to 0.
Okay, and then what do we do?
Each one is
Do the little dividing thingy.
What was that called when we made each one equal to 0?
factoring.
Yeah, factoring. We talked about graphing, right?
Which was terrible.
Where you had some kind of quadrant and you're looking for where it crosses the x-axis. We also had the quadratic equation.
I like that.
Yeah, I like that one too.
So, and we've talked too about how the degree, the highest power of the polynomial, determines how many roots there should be, right? Even if it means a root is repeated, a double root, a triple root, it's repeated. So the degree tells you how many you should have. Factoring is one method we've used, graphing, quadratic equation, but then there's other stuff, but I want to look at some patterns first. So let's take a look at this one. X to the third minus 5x squared minus 2x plus 24 equals 0. So I'm not going to make you go through right now and factor this. I'm going to give it to you in the factored form. So you can multiply it out if you don't trust me, but here it is. X plus 2 times x minus 3 times x minus 4, which equals 0. So this would give what roots?
Roots.
Well, you have to do the opposite of them. So you have
Right.
-2, +3, +4.
Right. So Hannah was saying the opposite of in here. -2, +3, +4, right? So, great. I'm curious. What's the product of 2 and 3 and 4? The product of those. What does that equal?
Oh, product of them.
Mm-hmm.
Wait, why not -2?
I'm just, for right now, there's a reason. Just look at the numbers themselves. I don't care about the sign for right now. 2 times 3 times 4, what does that give you?
24.
Right. Wait a minute. Look at your equation that we started with. What do you see?
Oh, you're supposed to see.
That's a 24 on it.
Oh, there is a
Oh.
24.
Okay. So all of these roots happen to have been factors of that constant term. Okay. What about if I look at another one?
That purple doesn't match.
What do you want?
The blue would be better.
This one?
Yeah.
Oh,
that would be
boy.
nice.
Oh boy. Okay, whatever. How about this one? 24x to the third minus 22x squared minus 5x plus 6. And I'm going to say that it equals in the factored form. This would be an ugly one to factor. You could do it. X plus 1/2 x minus 2/3 x minus 3/4. And I'm going to go through and highlight some things here, and then we'll talk. So I'm going to highlight the 24, and I'm going to highlight each of the denominators. And then I'm going to highlight the 6, and I'm going to highlight each of the numerators. So what are the roots?
The opposites of them.
Okay. Which are what? Negative 1/2, right? 2/3 and 3/4. If we look at the numerators and we look at the denominators each, what do you notice about those? So I'm gonna go through and look at
You
the
got
pink.
1, 2, 3, 2, 3, 4.
Okay. So they're in orders, great. What do you notice about what I highlighted in the original equation?
2, 3, 4.
What do you mean 2, 3, 4?
2, 3, 4 there.
No, sorry, this.
What?
this section. We're kind of focusing below the squiggly line for right now. Look what I've highlighted in pink. Look what I've highlighted in blue.
1, 2, 3, 1, 2, 3.
What's special about the pink 1, 2, 3 compared to the 6?
2 equals 6 every time them all.
Oh, if you multiply them all, you still get 6, right?
Mm-hmm.
So these are all factors of 6. What about the highlighted 2, 3, and 4?
It equals 24.
So each of these multiplied, you could say, are all factors of 24. You could even say they're each factors of 24, right? You can say they're all factors or each in this case, because if I use all of them, they'd still actually multiply to 24. But each one individually could be written as a factor. It'd be 2 times 12, right? Or 3 times 8, there's the factor. Or 4 times 6, there's the factor. Right? So we get into something called the rational root theorem. I'm going to try and leave this one on the screen while I write it. It's a lot of variables that don't maybe make sense unless you see it with numbers. So that's why I did all the number stuff first. So rational root theorem. So if Q over P. No, it is P over Q. I apologize. P over Q is in simplest form. No, there's reduced fraction. I hate that word, but simplest form. And is a rational root of the polynomial equation the first A, that's what we're putting the n there, x to the n plus a n minus 1 to the x, times x.
It's A?
A is just representing a coefficient.
Wait,
A sub n. So this one here is just some coefficient, a sub n, and then they're saying the next coefficient, a sub n minus 1. The powers should correspond. Let me make this one actually look like an n. N. So the power should be n, then n minus 1. Do you see that? And then if you continue the pattern going on, it'd be plus, oh, wrong marker there, sorry. Plus the first coefficient of just x to the first. I'm not going to even write to the first. We don't write that. Plus a sub 0, which is your constant, and that all equals 0. So if P over Q is in simplest form and is a rational root of the polynomial equation in this form, standard form, like what we just did way at the top of the screen right now, that was in standard form. The P over the Q, the 1 over 2, was a rational root. So if I go down to continue with what I was writing, with integer coefficients. All the A's are integers. I'm going to write that so you can read it. Then P must be a factor of a sub n, or sorry, not n, of a sub 0, the last one, the constant. And Q must be a factor of a sub n. I'm going to highlight these in the colors we were using above. So P must be a factor of a sub n. That was the stuff we highlighted in pink just above. And Q must be a factor of a sub n. That's what we highlighted in blue above. This is a whole lot of information here that's just making it complex, talking about what we just did there, giving it variable terms so it works for any situation. Does it kind of make sense, or do you need to see an example probably?
Let's see.
Let's try an example. Okay, example 1. Find the rational roots of x to the third plus x to the second minus 3x minus 3 equals 0. So for the first step is going to be listing the possible rational roots. And we do that by listing the factors of the constant over the factors, bless you, of leading coefficient. What are the factors of -3? Not a trick question.
-3 and 1.
Yeah, but you can say it could have been a 1 or a -1, right? So we say plus or minus 1 and plus or minus 3, because either case could have been a positive or negative, right? And then what's the leading coefficient up here? That's not written.
1.
1, right. There's a 1 there, an understood 1. So what are the factors of 1?
1.
1. Plus or minus 1, right? So we can combine these to give the possible roots. So anything divided by 1 is itself. So I kind of don't need to worry about this one, right? When the denominator is 1. So really we're focused on the positive and -1 and the positive and -3. So how can we find out if they're roots? Well, what happens when you plug in any of these numbers and it is actually a root?
It's going to be an imaginary row.
Nope. Remember, think about your graph. You're trying to find what x equals when y is 0. So if I put in a correct root, I should come up with 0 there. Yeah, that one. If I put in one of these roots and it gives me 0, it is an actual root. So test. A little bit of a pain in the rear end
Test
because
what?
you've got 4 different numbers to test. You've got a +1, a -1, a +3, and a -3.
Test
So-
possible.
Test the possible roots. So we have the original equation of x to the third. You might want to use your graphing calculator for this and put this into your y equals plus x squared minus 3x minus 3 into y equals y1. Then you can go to your table and you can say when x equals 1, what does y equal? When x equals -1, what does y equal? When x equals 3, what does y equal? When x equals -3, what does y equal? You can do that in the graphing calculator in your table, or you can take each one of these numbers and plug them into your equation. Yeah, really carefully so that you know that you're getting the right answer to see what y equals. Which way you want to do it?
Calculator.
Okay, plug it in quick. Because you're going to tell me what you get on these. Go to y equals.
I feel like I just charged this. And
I know, it's amazing. Y equals, type in x to the third.
Wait.
Oh, you have to turn it off. It is off.
What do you mean?
You're fine. Just go to y equals. Y equals.
Oh,
Clear
there
it. And then type in x to the third. Plus 2
Wait, I don't know how this one works. I always do these on the other calculator.
x to the third. And then arrow out of there. Yep.
X to the third
Plus
Plus-
x squared
x squared
minus 3x minus 3.
Then you go to the y equals, or this is the y equals.
Oh.
Then what are you going
Go to. Okay, so then you're going to go to the table, second graph. And you type in what you want. You want to type in 1 and press enter. -1. 3 and -3. So if you look here, 1 gave -4. -1 gave a 0. There's a root right there. 3 still gave 24, and -3 gave -12. So really the only root is -1. Okay? Does that make sense? Sort of.
No.
Go to your graph. Oh, go to standard window. Zoom 6. No, zoom 6. Oh. It's thinking.
It's loading.
I know. It's taking a very long time in doing so. Why?
Which one did you guys do?
This equation right here.
With the 1 in it?
Yeah, let me click
With
on
a
it.
1 in it. Let me
Wait.
see your equation.
I think I listened to you wrong.
Yeah, no, X here, where each of these is.
Yeah, this thing is probably gonna die.
X. Graph. So there we go. We've got a graph that looks like this. So here was your -1. So if I were to trace this, and go to X's. Oh, where's my trace? Where is it going? Oh, it's got a plot on. No wonder. Okay, here we go. So there's your -1. X is -1. Y is as close to 0 as my trace can get it.
Oh, that makes sense. Okay.
But then over here, there's another 0, but it's not a whole number. It's not an integer. And then there's another 0 over here. Again, it's not a whole number or an integer. It's between 1.1 and 1/3, 2/3, and 1.8 something. So somewhere in there, there's another root, but the only integer rational root was the -1, which is over here.
Hey,
Does that
it
make
works.
sense?
Finally loaded.
There you go. Okay. There's Hannah's just to show it. All right, thanks. Okay, here you go. So now you know you can use your table to plug them in. What were these? Go back to your table. Second. These were -4, 0, 24, and -12 when you used the table, right? Mm. Okay.
Oh, I get it now. It's
Okay.
exciting.
Good. We're gonna use it. We're gonna do example 2. Ready? Okay, example 2. Find the roots of 2x to the third minus x squared plus 2x minus 1 equals 0. Okay, this is where it's going to get really fun. So we still need to find possible roots. Where you're doing factors of your constant over factors of your leading coefficient. The first one's pretty easy. It's just positive, -1 are factors of -1. Possible factors of 2 are positive and -1 and positive and -2. So these together would give you, if I look at this pair, I need to make them into fractions that
Wait,
way.
where'd you get your +1, positive -2, and 1?
So the
Oh, it's your 2 and -1 right here.
the 1 that I just highlighted in blue was the factors of the coefficient at the end.
Okay. Those are
And then the factors on the bottom were the factors of the leading coefficient. I'm going to erase some of this highlighting down here. Okay. So we need to come up with the possible roots, in other words, the possible combinations between the top and the bottom. So I was looking at this first. So that still will leave me with 1 divided by 1, would leave me with a positive or -1 as possible. I also need to pair the top positive negative 1 with the bottom positive negative 2 to give me my possible positive, don't do that. I need pink. Positive or negative 1 over 2. Since they both were positive or negative, you still just have the one positive or negative. You don't need to put it on both. So literally this means I could have had a positive 1 or a negative 1. I could have had a positive 1/2 or a negative 1/2. Those are possible ones. You can use your calculator again if you want to, or we can try, I'm going to show you a couple different ways. Pardon me. Test 1. The number 1, right? So I could say 2, I'm following the equation, times 1 to the third minus 1 to the second plus 2 times 1 minus 1. So this
What are
one
you
we're
putting
testing
in? You're just putting 1 in
for all of the x's in the equation.
Okay.
This equation right up here, right? So we can figure out all that equals. 1 to any power is still just 1, right? So this whole thing should equal, does it equal 0 is what I want to find, right? So 1 times 2 is 2, minus 1 to the second is just 1, plus 2 times 1 is 2, minus 1. Simplify all that. 2 minus 1, 1. Plus 2, 3. Minus 1, 2. Did it equal 0?
No.
Nope.
So
that's not a
work.
root. Right. So this one did not work. We can try 1/2.
Wait, where are you getting these numbers? I'm confused.
From the possible list we came up with right here.
So we know it's going to be the negative 1, right?
We don't know.
Well, it has to be the 1 or the negative 1. And the
No,
one
it
didn't
doesn't.
work.
Remember in the one we just did? We had 4 possible numbers. A positive 1, negative 1, positive 3, negative 3. Only one of them worked.
Oh, you're saying there's an or in between here also then?
Sure, there's
Okay.
it's or
They're
any
all
of them.
any of them.
It could be and or. We don't know. That's why we have to test all of them. Do you see where I'm getting the test list yet from?
Sorta. I guess I see this. You're trying to get, you have like
Yep.
negative 1, but why are you choosing negative 1, not positive 1?
It's a positive and negative 1.
Oh, okay. I didn't see that. Okay.
Yeah.
Now
And then
this
same
makes
thing with
sense.
positive. You have to combine those. 1 over 1 is just 1.
Yeah.
1 over 2 is still 1 over 2.
Yeah.
And it's still positive or negative 1 over 2. Okay? And then we have to test each of them. So if we're going to test 1/2, I can go through the same process. Or I can use synthetic division. I'd like to do that as a reminder of how we do that. Okay, so remember we're going to take the coefficients of each of those.
Oh, is that the thing where they're on the brackets? and they're not?
So like the coefficients in front of here. Remember this?
Yeah.
I'm doing it as a kind of a reminder too. So we're testing 1/2. Then we're going to put 2. It's already in order and all powers are there. So 2, negative 1, 2, negative 1. We're going to bring down the 2. 1/2 of 2 is 1. Add those, we get 0. 1/2 of 0 is still 0. Add those, we get 2. 1/2 of 2 is 1. Add those, we get 0. So guess what? I
It
got
works.
0. It works. So this is a root, right? That worked. So we've tested 1. It didn't work. That's why I crossed it off. Positive 1/2. I did the top positive ones first. Positive 1/2 worked. We still have negative 1/2 to check and negative 1 to check. I don't care which way we do it. I kind of like the synthetic division, personally. You guys?
It confuses me so bad still, but
Then maybe
I
it's
like
good to
that.
practice it.
I like this one.
So let's test
I don't understand where everything goes on it. And that's what I still like. don't get that
test
thing.
negative 1/2. So I still have the 2, negative 1, 2, negative 1. I'm going to bring the 2 down. I'm going to try and use arrows for you. How about that, Hannah?
Okay.
You don't need to have
it's
arrows
below
normally.
line.
Negative 1/2 of 2 is going to be negative 1. Then I'm going to add these. going down.
-2.
-2. Negative 1/2 of -2 is a positive 1. I'm going to add those going down.
3.
And then I'm going to say negative 1/2 of 3 is negative 1 and 1/2. If I add those, do I end up with 0?
No.
No. I don't even need to go past that. Like, I don't care about the answers. I'm not asking you that part. I just want to know, does it equal 0? Pretty sure you can clearly see when you add those two, you don't get 0. You should get -2 and 1/2. We got one more to test. So the negative 1/2 didn't work. We need to test -1 also. Test -1. So we're going to put the -1 in the box, and you're going to use the coefficients again. 2, -1, 2, -1. Bring down the 2. I got 2. -1 times 2, -2. Add those. -3. Am I going too fast?
Almost there.
Almost there. -1 times -3. Bug. Okay, add those together. 5. -1 times 5 is -5. Add those, I still get -6. So this is not a root. I only had one root in all 4 of these. But that would at least allow me. I don't remember. Yeah, it will. We'll get there. This one becomes very helpful later on when doing synthetic division, because remember, we can rewrite this as a polynomial function.
So only
with
that
a degree
positive half
less.
worked.
Right, so we would have had the factored form of our original one so far. This would have given us a root. So we could have made that into a factor of x plus 1/2. With the remainder coming from here of 2x squared minus 2x plus 3. We're going to be using this eventually, because then we can find out possible factors of this to keep factoring further. It actually becomes a very useful tool. All right, we're going to keep going though. A while back, we talked about factoring using the quadratic equation, and that commonly produced what kind of solutions? Do you remember?
Irrational.
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 Yeah,
It
irrational.
really looks like an N.
So quadratic formula commonly gave us irrational roots that had a square root in them. In other words, irrational meaning they go on forever. They were still real, they just were not integers. They had decimals that just kept going. So something like if I had x squared minus 4x minus 1 equaled 0, and I used the quadratic equation, I would come up with 2 plus or minus a root of 5, which we knew meant 2 plus root 5 and 2 minus root 5. Remember that? These two paired together are called conjugates. The pair of numbers is a conjugate. This pair is called a conjugate pair. Or you could say they're conjugates or they're conjugate pair. Okay? Not too bad. So you see it, let's use it in algebraic form, whereas in like you could use it for anything. So here's the irrational root theorem. And you all thought you were done with theorems, but you're not. If I let A and B be rational numbers, and let square root of B be an irrational number.
Wait, what are rational, irrational?
Rational means like you can write it as a fraction. It's a terminating decimal, therefore it can be written as a fraction, or it's a whole number or an integer. There's no like pi is irrational. It keeps going on forever and ever and ever without patterns, without repeating. So irrational is that without repeating, without patterns, cannot be written as a fraction. Okay? So like the square root of 2, square root of 5, square root of 3, square root of 7, things that are not perfect squares will produce irrational numbers. They just keep going forever. Okay? So if I have some rational number, like 1/2, or 3, or -10, and I add to it, like up here, the square root of a rational number, this part would produce an irrational portion added to a rational that still gives you an irrational number. Okay? Let a and b be rational numbers. Let square root of b be an irrational number. So then we can then say if, that should be capital, if a plus the square root of b is a root of a polynomial equation with rational coefficients, nothing that goes on forever, no square root coefficients, then the conjugate of a minus square root of b is also a root. I'm pointing out the slight difference between these two. So if we say a plus the square root of b is a root, then a minus the square root of b is also a root. That's all they're saying. You can start it the opposite way too. If a minus the square root of b is a root, then a plus the square root of b is a root. It's not super complex, although it's made to look like it's super complex. It just gives you this up here. When you came up with the quadratic equation, we solved using it. We had two roots that looked identical other than the plus or minus in the middle, right? Now there's a theorem that says that. Okay? Example 3. A polynomial equation with integer coefficients, I don't even need to know what it is, has roots 1 plus root 3 and negative root 11. So I know that those are two roots. Find two additional roots. I'm going to apply the theorem we just talked about.
Where's the A and the B?
A, B. So if I have a 1 plus root 3, what's its counterpart, the conjugate of it?
The
1,
opposite?
yep, minus root 3. There's one of the next roots. And then this one, a little trickier because where's A?
There's no
No
A.
way.
What could A be?
It could be plus or.
And what can A be?
0.
0. It could be 0, right? If you need to think of it as A plus or minus root something, B, right? A could be 0, right? If that helps you. So if I take, wrong thing, and I go over here, what's the other root that would go with negative root 11?
Positive root
Yeah.
11?
And we don't have to put the positive, we just say root 11. So there's 1, there's 2 additional roots. Totally not meant to be super difficult. Those are your possible roots. So you have 4 roots, therefore what was your equation? What degree?
Find 2 more roots and we found,
Fourth degree?
Yeah, it was
Fourth
4th degree. There were
degree.
4
Four
roots.
intercepts?
Yeah, there were 4 roots. It's a 4th degree equation. Okay.
Whoa. I feel like my eyes.
Yeah, the printing on the page was not good.
Whoa. It's terrifying. That looks like a migraine.
Okay. Complex conjugates. What are complex numbers? Do you remember?
complex, are those the ones that are imaginary?
Yeah, they are. Complex number includes an imaginary component. So we can have complex conjugates. It's ever so fun to spell conjugates, isn't it?
Wait, it says complex numbers include imaginary.
That was numbers, an imaginary component. So something like 3 plus I root 2. That would be an imaginary or a complex number. This is a complex number. If I have complex conjugates, let's say I have this, the one I just had there, 3 plus I root 2, what would the conjugate of that be? if you think about what we just learned about conjugates in general, like these
It would
two
be
here.
the opposite, so it would be 3 minus I
Root
root
2.
2.
Yeah. And if we were to use it algebraically, I'm just going to write the theorem for it. So it's the imaginary root theorem. Doesn't feel as complex as the other one, what I'm going to try. If the imaginary number a plus bi is a root of a polynomial equation with real coefficients. In other words, no square root of negative numbers as your coefficient. Then the conjugate what would the conjugate of a plus bi be?
A minus B.
Yep. Then it's also a root. Okay? Not too bad. We'll try a quick example, a very quick one with this. I'll leave the theorem even there. A polynomial equation with integer coefficients has the roots 3 minus I and 2I. Find 2 additional roots. What would...
So you can do the 3 minus I is 3 plus I.
Yeah. The conjugate of 3 minus I is 3 plus I. And then what's the conjugate of 2I?
Negative 2I.
Yep. It's totally not meant to be incredibly difficult, right? So I have 1, 2, 3, 4 roots. It's also another 4th degree equation.
Okay, I'm there.
Okay? Hey, and look at that. Critical thinking for the check understanding is exactly what I've been doing. Describe the degree of the equation. I've been doing that already with you. What do you know? All right, last example. Writing a polynomial equation from its roots.
So you're just going backwards?
Mm-hmm. So, like, if you're to trace your roots, you'd be going up, down your family tree to figure out where you came from in history, right? So you're going backwards. Same idea like what Hannah just said. So if I have polynomial of 3rd degree has integer coefficients and has roots of 3 and 1 plus I. So what are all of the roots then? Do we have all of them listed yet?
No, you only have 2 of them.
Why? What else do I need?
Negative 1
The
and
negative.
Yep. 1 minus I. Right. So now I have 3 roots, which would be that 3rd degree part. So there's 1 root, 2
How
roots,
do you know
3
it's
roots.
not the 3 one?
What?
Like,
Wait,
how do you
why
know you
didn't I
don't
do
change the
negative
3?
The 3 is just it's not a conjugate. It's not a complex number. It's not the ones
It
we were
doesn't have
talking.
an I.
Right, and it's not the ones where it had up above the square root part of it, right? It's
Yeah.
just a standard integer number. So each of these circled pink things translates to a bubble, some longer than the others. So we'll do the harder one first. X, what, 3?
minus 3.
Why is it minus?
Because it's always opposite.
Right. And then the next one is a little bit more complex because we're talking about the I one. So,
1 minus.
so X minus the whole thing of 1 plus I, and X minus the whole thing.
1 minus I.
Yep. So we need to simplify and then multiply everything out eventually, slowly. We'll do it step by step, right? So this negative needs to be distributed, as does this one and this one. Okay? So let's work on that part. So I would have,
Oh, you put them all in individual bubbles in the bubbles. I didn't do that.
they didn't even do that. You know what, we're not gonna do, I'm gonna follow their steps. Forget it. We're not gonna distribute that. I'm just gonna leave it as, we need to FOIL. We need to say x times x, right? I'm gonna leave this first factor alone for right now. It's the easiest one, it'll be easy to take care of at the end, okay?
Wait,
X
which
times
one
x.
are you doing? I can't see where the bubbles all end on yours.
So I'm not worried about the x plus minus 3 yet.
Okay.
I'm gonna look at the next 2 bubbles. If it's easier to put brackets in here, you can. There's nothing wrong with that. It just kind of helps your eyes see the difference. So to FOIL this, I need to do first times first. X times x is x squared. Outer times outer minus x times 1 minus I. I'm just doing the whole thing for right now, leaving it like that. And I'll distribute in a little bit. I is inner times inner. X times negative, so it'd be a minus. X times 1 plus I. And then I have my lasts. And it's a negative times a negative.
Wait,
So
your last one is 1 plus I?
yeah, because that was right here. And then the 1 plus I, but the negative 1 plus I times the negative 1 plus minus I. So I would have plus 1 plus I, 1 minus I. And then we need to do some more distribution and more foiling. This last part will need to be foiled. These each need to be distributed, right? And I still have, this just gets carried down. X minus 3. I'm going to still just carry down the x minus 3 for right now. X minus 3. I'm sticking it there so don't forget about it. The x squared doesn't get simplified, but this negative x gets shared. So negative x times 1 is negative 1, negative x. Negative x times negative I is positive xi. Ix, I guess, because I is considered a number, not a variable. Ix. And then again, negative x times I, or times 1, negative x times positive I, negative ix. And then this needs to be FOILed, this part here. 1 times 1, peanut gallery.
1.
1. 1 times negative I,
Negative I.
I times 1,
I.
negative I times positive I,
Negative I.
negative I squared, right. Okay, simplify more. Let's combine some like terms within this section. What do you see?
Bunch of x's.
Yeah, a lot of x's. Is there anything like an x squared in there?
No.
Okay, so I'm going to write that one down, x squared, and I'm also going to write the first factor, x minus 3. How about an x term? Are there any more x terms?
Yeah.
Yeah.
Okay,
There's 2 of them, 2 negative x's.
but ones that don't have I with it.
Yeah,
Yeah.
these two, there's 2.
Right, so you got the negative x and the negative x.
Yeah, so
So you
negative.
should have negative
2.
2x. Then we have a positive ix and a negative ix.
Those will cross out.
Right. Wonderful. Then I have a plus 1. And then what about these two? Negative I, positive I.
Negative I, positive I, cross out.
Cross out.
Right. And then I have negative I squared. What is I
Negative
squared
I
equal?
times negative I.
What's I equal to?
Oh, negative I squared equaled 1, right?
Negative 1.
Negative 1.
Because it was the square root of negative 1 times the square root of negative 1, right? And square root times square root gets rid of itself. So I have negative 1 times negative 1, which would give you...
Wait, this is a positive one, I thought.
I'm looking at just the negative I squared. Just the negative I squared. So I took the negative out front. That's this negative here is what's right here, the negative 1. The I squared was the square root of negative 1 times square root of negative 1. Square root times square root is just whatever's inside. So there's the negative 1 times the original negative 1 from outside, which would give you a positive 1, right?
Mm-hmm.
So I still have a positive 1.
What about that 1 that was right there?
I just didn't add it. It's still there. It's right there.
Oh, so you have 1 plus 1 then.
Yes. So the
You'll
1
have
plus 1,
2.
right, so if
Your
I,
2 will go over
instead of
there.
crossing off, I'm just going to rewrite x minus 3, x squared minus 2x plus 2. Okay, now we need to distribute the first factor, x times everything inside. Have I ever shown you guys the vertical method of doing multiplying this like this? For the fun of it, I want to show it to you. X squared minus 2x plus 2. And so it's kind of like saying 17 times 3. You say 3 times this part and 3 times this part, right?
Mm-hmm.
I'm going to do the same thing below here and write the second factor of x minus 3 here. And we're multiplying, right? Multiplying this, yeah. So I'm going to say 3 times each part. And then I'm going to do x times each part. So 3 times 2, negative 3 times 2 is negative 6. Negative 3 times negative 2x, positive 6x. Negative 3 times x squared, negative 3x squared. Then I'm going to switch colors as you can see what I'm doing. X times 2. Well, I'm not going to put it directly below the 6, just like when you're doing like 13 times 17, you'd scooch over a spot, right? Do the same thing here. X times 2 is 2x. X times negative 2x is negative 2x squared. X times x to the third is, sorry, x times x squared is x to the third. So then when I go to add these, there's nothing to add here. So it's just negative 6. And 6, oh, this was a positive, wasn't
6
it?
plus 2x.
Yep.
6x.
Is 8x. And then I have a negative 3x squared and a negative 2x squared, so a negative 5x squared. That x, there you go. And then
Plus
x to the third.
3x.
Yep.
X to the third. And here.
Yeah. So the signs in front of them serve as the plus or minus. So there's your final multiplied out polynomial incorrect form from the original roots given. Right?
That's a long equation.
It is long mainly because you had complex roots. And those complex roots, when you multiply them out, are complex. There's lots of different aspects to consider.
Yeah.
Okay? Any questions on this?
Not at the moment.
Okay, good luck on your homework. Thanks for joining me.